Let me know. Okay, then let's start into the last two sections. This section is called the chain rule. Okay, that's 1.7 is the chain rule. And it's what happens when we have a function inside a function, kind of like function inception. And we want to take the derivative of that. So we have to take the derivative of the outside and the derivative of the inside. Okay, so we kind of have to do derivative inside derivative. And so 1.7 is called the chain rule. Okay, and so we say for f of g of x, notice that there's a function inside a function, the derivative is given by f prime of g of x times g prime of x. So we do the outside function, and then we do the derivative of the inside function. We multiply the two together. So it's always outside, derivative of outside times the derivative of the inside. Outside times inside. Okay, let's see how this works. Okay, I have the derivative, okay, 1a here, of f of x equals 1 plus x cubed to the 1/2 power. We're going to take the derivative of the outside function. So we want to think of this thing that's inside the parentheses as just one item. Maybe we'll call that u. Okay, we'll say u is equal to 1 plus x cubed. Okay, so this is really, we want to take f of u. Don't say that at home, okay, because you're going to get in trouble. Okay, I can say it because I'm a mathematician. I can say f of u. Okay, but don't say that to your mom because she'll smack you. Okay, but f of u, she's not going to know what you're talking about. Just think that you're saying something else. Okay, so f of u is equal to u to the 1/2, right? So if I were to take the derivative of this, okay, that would be 1/2 u to the negative 1/2, right? And that's what we're doing. We're doing the derivative of the outside function. We're treating this as one item, do the derivative of the outside function. Then we have to multiply that times the derivative of the inside function. Well, what's the derivative of the inside function? What's our u? Say our u of x here. Our u of x is 1 plus x cubed. So what's the derivative of that? Well, that's just u prime of x, which is 3x squared. So I would have to take this, and it would end up looking like this: 1/2 u. But what was u? U was 1 plus x cubed to the negative 1/2 power. Okay, that's what this thing is. Okay, times u prime of x. Well, what was the derivative of the inside? It was 3x squared. Now, I don't do this whole u thing, what's called a u substitution. We don't do that u substitution every time. We just kind of in our mind do that. Let me show you how I would do this just without the explanation. So if I have 1 plus x cubed to the 1/2, well, what am I going to do with this 1/2? I'm going to drop it in front. That becomes 1/2 times 1 plus x cubed to the negative 1/2, right? Times the derivative of the inside. So derivative of outside times derivative of inside times 3x squared. Oh, okay. Because the derivative of constant is 0. It just goes to 0. So this thing is equal to 3x squared over 2 times the square root of 1 plus x cubed. Okay. So we could write it like that, or we could have left it as 1 plus x to the 1/2, because that's the way they gave it to us. Either way. Okay, so derivative outside, derivative inside. That's the chain rule. Okay, so it's just like a chain of events that's happening. That's why it's called the chain rule. Okay, you do the derivative here, then you do the derivative here. And then if you had, say you had 3 functions inside, so a function inside a function inside a function, you'd do derivative of outside function, derivative of middle function, and then derivative of the innermost function. And then you would just string them all together as you multiply. Okay. Okay, let's look at B here. B, y is equal to 1 minus x squared cubed plus 5 plus 4x squared. Okay, so once again, we're going to take the derivative of this. I want to take the derivative of the outside times the derivative of the inside. This is going to be chain rule in the first term. This is y prime is equal to 3 times 1 minus x squared times the derivative of the inside. Well, what's the derivative of the inside? What's the derivative of 1 minus x squared?
2x, 1.
Close. Close, Mario.
Is it
Negative 2x.
Negative 2x.
yeah, negative 2x, yeah.
Thank you, Yusuf, and thank you, Mario, again. It's negative 2x. Good job. Okay, plus derivative of the outside here is going to be 2 times 5 plus 4x to the 1. Okay, and then what's the derivative of the inside?
4.
4, yeah, very good. Thank you, Mario, again. 4. Okay, so let's clean this up a little bit. Okay, negative 6x times 1 minus x squared squared plus 8 times 5 plus 4x. I could leave it like that. I could also distribute if I really wanted to. I don't want to distribute this thing because that's going to be a pain. And I'm not going to get much return on my investment there. Remember, to simplify means to make it simpler, not more complex. So I might just go negative 6x times 1 minus 8x squared squared plus 40 plus 32x. And I'll probably just leave it like that. Okay, now this one, you kind of need to make special note of this. You are going to have one like this on the study guide and possibly on the exam. So I'm going to put a little asterisk next to C here. This one is it's kind of neat the way it works, at least in my opinion. Which take that for what it's worth. So 3x minus 5 to the 4th times 7 minus x to the 10th. Okay, so this is a chain rule and a product rule all nestled up together. Okay, so let's see what we can do here. Let's do the product rule. Let's call this maybe a of x. Let's call this b of x. Okay. So to find the product rule, I would need the derivative of the first. So let's take the derivative of the first. That's a chain rule. That's 4 times 3x minus 5 to the 3rd times 3. Times the derivative, that's the derivative of the first times the second. So all I'm going to do now is just multiply by the b of x. That's 7 minus x to the 10th power. Plus the derivative of the second. Now I've got to do the chain rule on the second one. So this is 10 times 7 minus x to the 9th power times negative 1. Where'd that negative 1 come from? It just magically appeared.
From the negative x inside the parentheses.
Yeah, exactly. That's the derivative of the inside. It's the derivative of the negative x, which is negative 1. Okay, times the first, which is 3x minus 5 to the 4th power. And this is f prime of x. Now, I'm not going to leave it like this because I can clean this thing up a lot. Okay. So what is this? This is 12 times 3x minus 5 cubed times 7 minus x to the 10th plus, or minus, I'm going to go minus on this one, minus 10 times 7 minus x to the 9th times 3x minus 5 to the 4th. 3x minus 5 to the 4th. So now what I'm going to do is factor out the common factors here. Okay, factor out the common factor from the first one and the second one. Well, 12 and 10 are both divisible by 2. So that's a common factor there. 3x minus 5 to the third and 3x minus 5 to the fourth are both divisible by 3x minus 5 to the third. It's the lowest power there. I'm going to pull that out from the first one. Okay. And so what's left over, I'm going to put some parentheses here, is 3x minus 5 minus 1. Okay. So I get a 3x minus 5. Actually, it's the other way around. Sorry. It's going to be 1. And then over here, it's minus a 3x minus 5. 1 3x minus 5 is left over. Okay. Okay. The other thing that I can factor out is a 7 minus x to the 9th power. So this is going to be 7 minus x to the 9th power. And what does that leave behind? Well, that leaves behind 1 7 minus x. So this becomes 6 times 7 minus x. That's what's left over in this first term, minus 5 times 3x minus 5. That's what's left over in the second one. Oh, minus 15x plus 25. Okay. So this becomes 2 times 3x minus 5 cubed times 7 minus x to the 9th times 67 minus 21x. And that's it. We get 4 terms for our derivative. It's kind of nice. Okay, we get a function that has 4 factors. Something's going on here with my sharing. Let me stop my sharing for a second. Let me share my screen again. For some reason, it was lagging. I don't know why that was. It's kind of weird. Can you guys see my screen?
Yes.
Yes. Okay, good. Okay. Sounds good. Thank you. Okay. Something's going on with this thing. Kind of weird. Whatever. Okay, let's go on to the next example here. Okay, let's look at the reason why this is such a nice exam problem is because it tests more than one property. This tests not only the product rule, but this also tests the chain rule. So you get basically two, kind of like a 2-in-1. You know, do you know the product rule and do you know the chain rule? And so this is, again, this is kind of like how professors like to write their exams is, you know, oh, I can kill 2 birds with 1 stone by testing them on 2 concepts instead of 1. Okay. Okay. Okay, let's look at D here. D is also a really nice problem. Okay, f of x is equal to the square root, or the 4th root actually, the 4th root of x plus 3 over x plus 2, and we want to find the derivative of this thing. Okay, so let's see what we got here. So I want to do the chain rule. I'm going to take f of x and I'm going to it's going to equal x plus 3 over x plus 2 to the 1/4 power. I'm just going to change it to an exponent. Okay. And then I'm going to do the chain rule here. This is going to be 1/4 times x plus 3 over x plus 2 to the negative 3/4 power times the inside. Anybody know what we're going to have to do on the inside? What rule are we going to have to use on the inside?
Is that the quotient rule?
Yeah, very good. Thank you. It is the quotient rule. Thank you, Mario. Okay. Yeah, we're going to have to do the quotient rule. So derivative of the top, 1, times the bottom, x plus 2, minus derivative of the bottom, 1, that's kind of nice, times x plus 3, all over the derivative of the bottom, which is x plus 2 squared. Oh, okay. Very good. Very good. Okay, this is equal to 1/4 times, now, does anybody know what I can do with a fraction raised to a negative exponent? Anybody know what I can do with that? A fraction raised to a negative exponent. By the way, oh, here, Yusuf, here's my Star Wars shirt for the day.
Stormtroopers and Vader.
Yeah, and Vader, exactly. So there's the Star Wars shirt for the day. Okay, so
Good to see.
my daughter, she says, how many Star Wars shirts are you gonna own? And I'm like, I don't know, I need one for every day of the week. So there you go.
Not a bad idea.
I know, right? It's like, oh, that's my Tuesday shirt.
Exactly.
Like I teach from home, why do I need to dress up, right?
Yeah, exactly. Agreed.
Star Wars shirt for Monday and a Star Wars shirt for Tuesday and a Star Wars shirt for Saturday. And maybe one for Yom Kippur or something. I don't know. Just there's always an excuse to buy a Star Wars shirt. Okay? There's just it. Late Arbor Day. I mean, come on. Who doesn't have a Star Wars shirt for Arbor Day?
Yeah, you're not wrong.
Right. I mean, come on. You know, I gotta get mine with a little baby Yoda with a little Santa hat on it.
Oh, okay. That'd be interesting.
Yeah, it would be. I'm gonna special order that one for Christmas.
Yeah, perfect.
Okay, so what we can do with a fraction raised to a negative exponent is we can just flip that sucker right upside down. This thing just becomes x plus 2 over x plus 3 to the 3/4. Boom. That's easy. Because it's really 1 over a fraction, and what happens when I take 1 over a fraction? It multiplies by the reciprocal. So it just flips. It flip-flops. Right? So we're going to get up here, it gets real nice too, because what happens to the x's when I distribute this negative sign, the x's, this becomes x plus 2 minus x minus 3 all over x plus 2 squared. So the x's cancel out. Wish my x's would cancel out. Anyway, that's a personal issue. Okay, so negative 1 over x plus 2 squared. Okay, we got that. So let's see what else we got going on here. Okay, plus 2. Oh, is it? It's plus 2. No, it's plus 2. It's good. Okay, and then I think that's, oh, look at this. Look at this. We've got an x plus 2 on the bottom, and we've got this funky thing going on, x plus 2. So let's do this. Let's do 1/4 x plus 2 to the 3/4 on the top. This is going to be a negative, because that negative 1 I'm just going to pull over. And then this is x plus 2 to the squared times 1 over x plus 3 to the 3/4 power. Now, there's a reason I did this, because now I can subtract the exponents for x plus 2. This becomes negative 1 over 4. 2 minus 3/4, that's 1 1/4 or 5/4. Okay. So this is going to be x plus 2 to the 5/4. Okay, all over x plus 3 to the 3/4. Okay, and since I was given the problem as a fourth root, I'm going to put the problem in that form as an answer. So this becomes negative 1 over 4 times the fourth root of x plus 2 to the 5th times the fourth root of x plus 3 to the 3rd. Oh, okay. And I can put it all under 1/4 root because they're both to the 4th root. And that's it. That's my answer. Well, that's kind of a nice one. Interesting. Okay, so that's what happens when we do composition of functions here. Let's talk about composition of functions real quick. Okay. Because that's really what we're working with, is composition of functions. We're working with a function inside a function. How did the 3/4 become positive? Yeah, it's kind of an algebra trick there. If I do 3/4 to the negative 5th power, right? Well then, how can I relate this? Well, this is going to be 1 over 3/4 to the 5th power, right? Which is equal to 1 over 3/4, 3 to the 5th over 4 to the 5th, right? Which is really 4 to the 5th over 3 to the 5th, which is really 4 over 3 to the 5th. Boom. So what would a fourth grader say that I did there? They would just say, oh, you just flipped it upside down. Does that make sense? So because it was negative, I flipped it upside down and made it positive. Sounds good. Okay, let me take a water break for 1 second. I'm getting a little parched. I'll be back in 60 seconds. I need to go get some water. Be right back. Go. This is a water checkpoint. Get yourself some water, and I'll meet you back here in 60 seconds. Okay, I'm back. Okay. Oh, sorry. I got some Skittles too on the way. They were there. I just had to grab a handful. It was a need. It was a necessity. So taste the rainbow. Taste the rainbow. Oh, so good. Yum. I'm gonna put them on it, yeah. Hashtag no spawn. No spawn. All right. No. No spawn. Although, are you concerned about internet security? I'm just kidding. No commercials. No commercials. Okay. Have you ever tried NordVPN? Okay. Hashtag no spawn. Okay. Okay, composition of functions. Okay, so f of g of x can be rewritten is written as, okay, f of g of x. Okay. So, number 2. For f of x is equal to x to the 4th, and g of x is equal to 2 plus x cubed, find a f of g of x. Okay, so what does this mean? This means that we want to do f of g of x, which means that every time I see an x in f of x, I want to put in g of x. So let's think about this. This would be f of g of x. Okay, so what does that mean, f of g of x? That means that this is going to be equal to g of x to the 4th power, right? Does that make sense? Okay, so that's g of x to the 4th power. Why is that? Because f was x to the 4th power, and I'm just replacing x with g of x. Okay. Okay, but what was g of x? Well, wasn't that 2 plus x cubed? So this thing, f of g of x, is equal to that. Oh, okay. Let's do it backwards here. Let's do g of f of x. What does that mean? It means g is on the outside and f is on the inside. Okay. Well, that's g of, what's g? G is 2 plus x cubed. And every time I see an x, I'm going to replace it with f of x. So f of x cubed. Okay. But what is f of x? It's x to the 4th. So this is 2 plus x to the 4th cubed. And raising a power to a power is x to the 12th. Oh, okay. So that is g of f of x. Okay. Okay, number 3. For f of x equals radical x, and g of x equals x minus 1, find f of g of x and g of f of x. Okay. So f of g of x means start with f and then plug in g of x. Whoosh, right there. So that guy is going to be the square root of x minus 1. Okay. And what's g of f of x? Well, that means start with g and plug in f. Whoosh. So that's going to be radical x minus 1. Okay, let's do a real life example here with these. How many flavors are there in Skittles? 1, 2, 3, 4. Looks like there's 5. Oh, sure. Okay. While you write that down, I'm gonna pound some Skittles here. Okay, I got green, yellow, orange, red, and purple all at once. I'm literally tasting the rainbow. Okay, it's literally what's gonna happen. Okay, 3, 2, 1. That was amazing. You need to try that. That's so good. Yeah. That's some good stuff. All right. Let's get back to the math. You're like, I'm not here for the skills, bro. I'm here for the math. Let's get back to the math. Okay, number 4. Okay, business. Okay, business rate of profit. Okay. Okay. A computer software store. Do they even have those anymore? Computer software? I guess that's big Best Buy. Computer software store. Okay. Maybe it's a gaming store. Who knows? Whatever. This is all hypothetical stuff anyway. Okay. Okay. Has a profit function in dollars given by P of U, okay, is equal to 0.1 U squared minus 500, where U is the number of units sold. Okay. This is a really obnoxious function, okay? Because it stinks. This function stinks. Why does this function stink? Any ideas? Because it's P of U. It's PU. Dad jokes for days. Okay, dad jokes for the win. Okay, so PU. Get it? There you go. Exactly. Thank you. Thank you for the pity laugh, Oscar. I appreciate that. Okay, so PU, which is the profit of the units sold, right? Stinky little function. Okay. Okay. Its sales are given by, okay, u. So now u is going to be a function of something else. P is a function of u, but u is a function of x. Oh, okay. So the units, excuse me, the number of units sold are based on the number of days, I guess, after the store is open. Okay. So the profit changes day to day based on how long this is open. Okay, and that is u is equal to, we're going to call this g of x or u of x. Maybe we'll just call it u of x. U of x, okay, which is equal to 125x plus 40. Let's go. Let's go. Where x is the number of days the store has been open. Okay, find the rate at which the profit is changing on the 5th day. Okay, so we need to know what's the change in profit. Well, that's going to be P prime of u, right? P prime of u. But what was u? Well, this is not just u, this is u of x. So this is going to be the derivative of P of u of x, right? So this is a function inside a function. So we want the derivative of a nested function. So that's going to be the chain rule. Okay. So this is going to be equal to P prime of u of x times u prime of x. Oh, okay. So what was P? Well, P was equal to 0.1 u squared minus 500. Okay. And so what's the derivative of that thing? Well, that's just going to be 0.1 times 2u. The 500 goes away, so that's P prime is equal to this, right? Okay, but I have to multiply that by u prime. That's a u. Times u prime of x. Well, what was u of x? What was u of x? U of x was equal to 125x plus 40. So what's the derivative of u? What's u prime? Well, that's just 125. So this is times 125. So P prime, okay, of u of x is equal to, okay, it's the derivative of the whole thing. Okay. I'm just going to put P prime. Okay, P prime is equal to 125 times 0.1, so that's going to be 12.5 times 2 is 25u, I believe. Do that right? Oh no, 125. This is 125. No, that's right. Let me see.
Yeah, I got 25.
You got 25 as well? Okay.
Yeah.
Let me just make sure we're all on the same page here.
Did you multiply by 2 after multiplying by the 0.1?
I did.
Okay, thank you.
Sure. Yeah, that's right. That's right. Okay, but what is u? What is u in this case? Well, it's this original thing, right? So p prime is equal to 25 times. I want this in terms of x, because that's what the derivative was, d dx. Is going to be 125x plus 40. Okay. And so I could distribute this, p prime of x now, p prime of x, is equal to 25 times 125. What is that? 25 times 125. 3125 x plus, okay, 40 times 25. That's 1,000. Okay, and what do I want? I want the profit on the 5th day. So we want p prime of 5. 3125 times 5 plus 1,000. 3125 times 5 is 15,625 plus $1,000 is 16,625 dollars. That's the profit that I would have made on the 5th day. Okay. Or that's not the profit I made on the 5th day. That's how fast the profit. 16,625. That's how much the profit went up on the 5th day. So the profit is changing by $16,625 per day. That's the rate of change, okay, on the 5th day. Okay, so the rate of change isn't always constant. It depends on what day you're at, depends on where you're at. Because you could say that your profit function, and this is days, and this is profit, okay, maybe X is days, and you're gonna have your profit, you know, on day 1, 2, 3, 4, you know, 5, 6, okay, and so maybe you start off low profits and then you start going up, right? Going up. And so the profit here is different than the profit here. It's dependent on the day, and the rate at which the rate of change is the tangent line, is the slope of the tangent line. Maybe you're faster here and you're slower there. But in this case, the profit always keeps going up. Okay, so that's why there's a positive change in the profit. Okay, it could also look like this. It could look maybe like this, where you have low profits in the beginning and you have a higher profits later on. Okay, and so over one day, what was your average rate of change for that day? Well, the average rate of change over one day was $16,625. That's how much your profit increased. Okay, profit is, maybe I'll put increasing, because it's a positive number. This is a positive number, so I know it's an increase. If it was a negative number, it would be decreasing. The profit would be going down. Okay, let's do another example here. Let's do example 5. A new smartwatch is placed on the market. Okay, its quantity sold is N units or N watches. Quantity sold is N watches and is given by N of T equals 250,000 T squared over 2T plus 1 squared, where T is greater than 0 and T is time in weeks. Okay, T is time in weeks. Okay. We want to find how fast the number of watches being sold is changing after 1 year and after 4 years. Okay, so that's what we want to do. We want to find out how fast is the number of watches being sold changing after 1 year and after 4 years. What's the instantaneous rate of change per watch? Okay, what's the rate of change per watch? Okay, so we need to find the derivative here and then plug in the value. So quotient rule, right? We're going to work with this thing here. And so we're going to want to use the quotient rule. So n prime of t is equal to the derivative of the top. That's 250,000 times 2t. That's the derivative of the top. Times the bottom, 2t plus 1 squared. Minus the derivative of the bottom. Now the derivative of the bottom is a chain rule. So that's going to be 2 times 2t plus 1 to the first power times the derivative of the inside, which is 2, times the top, which is 250,000 t squared, all over the bottom squared. Well, what's a squared squared? Well, that's just to the fourth power. It's going to be 2t plus 1 squared squared. I'll try not to skip steps. Okay, so this is going to be 500,000 t times 2t plus 1 squared minus, this is going to be 4 times 250,000, that's 1 million. 1 million t squared times 2t plus 1 all over 2t plus 1 to the fourth power. Okay, so what I can do is I could factor some stuff out here. I could factor out a 500,000 t, and I could factor out 2t plus 1. And what I would get left over is a 2t plus 1 minus t, oh no, 2t, right? Minus 2t. I think that's it. Minus 2t, yeah. All over 2t plus 1 to the fourth power. Okay, so the 2t's are going to cancel out. that just leaves me with a 1 on top, times, and look at this, one of these two t's plus 1s are going to cancel with one of those, leaving me with 3. So this whole thing reduces or simplifies to 500,000 t over 2t plus 1 cubed. Okay, so that's n prime of t. Okay, that's kind of cool. That's the instantaneous rate of change after a certain number of watches are this is the instantaneous rate of change of the number of watches sold after t weeks. So let me write that out. Instantaneous rate of change in watches per week of the number of watches sold after t weeks. Okay, and so what does the original function kind of look like? It kind of looks like this. Right, and it's kind of like after a certain number of weeks, we're really not selling that many more watches, right? Kind of like the total number of watches sold kind of plateaus there. Okay, so that's kind of like what's happening with this thing. Okay, but we're interested in what's going to happen after 52 weeks, which is 1 year, and after 208 weeks, how fast are the watches changing? What's the rate of change in watches per week? So all we have to do is plug these numbers in to the derivative, and we'll calculate. N prime of 52 is equal to 500,000 times 52 all over 2 times 52 plus 1 cubed. So I plug that into my calculator. Let's do that. Let's plug this into the calculator. Okay. Let's see if we can do it on this one. Although I don't really like this calculator. Okay. So let's calculate the bottom first. Well, let's just calculate the top. That's easy. 500,000 times 52, that's 26 million. Okay, that's the top. Let's clear that. Okay, 2 times 52 plus 1. What's 2 times 52 plus 1? That's 105. Raised to the third power, that's going to be huge. Raised to the third power, boom, that's 1 million. 1,157,625. Oops, that wasn't right. 157,625. Okay, and then we're going to divide those two numbers, which comes out to about, okay, about what? So 26 million divided by 1,157,625. Okay, and I'm getting about 22.5 watches per week. Okay, that's about how many watches I'm going up per week. Okay. Let me stop my share for 1 second. Okay, now it's popping up. That's good. Okay. What about after 4 weeks? What about after 4 years? Well, what's n prime of 208? Well, we'll just do the same thing. 500,000 times 208 over 2 times 208 plus 1 cubed. And I'll just tell you what this is. This comes out to be about 1.4 watches per week. So not a lot of watches being sold every week after 4 years. Okay, so again, it kind of makes sense to the graph that I showed. We're not going up by many watches every week after 4 years, but we are selling around 22 to 23 watches per week after 1 year. Let's look at 1.8 real quick. Okay, we're going to come back to this example, okay, in a little bit. Okay, so just keep that in mind. We're going to come back to here in a little bit, but let's go into 1.8, which is higher order derivatives. Okay, higher order derivatives. That means that we have f of x, and then we have f prime of x, and then we have f prime of x, which we say is f double prime. Okay, that is taking the derivative of the derivative. Okay, so we could say that d dx of f of x is equal to f prime of x. And if we take the derivative of f prime of x, then we say that that's the second derivative. Okay, so this was the first derivative. And this guy here is the second derivative. Second derivative. Okay. F double prime of x. Okay. We could have an f triple prime of x if we wanted to. We could have an f to the fourth. Now it's not to the fourth power. This is the fourth derivative. We put it in parentheses like that. That's fourth derivative. And you can just go all the way down, right? You just be like the nth derivative of x. Whatever derivative you're looking for. Okay, sometimes the first derivative is dy dx. We call that dy dx. That's f prime of x. To the called Leibniz notation, which you don't really need to know that, but it's d 2y over dx squared. Okay, d2y, that's f double prime of x. Okay, this is Leibniz or Leibniz notation. Okay, this guy over here is Newtonian notation. Newtonian notation. Okay, so these two guys were bitter rivals. Okay, Leibniz had his notation and Newton had his notation, and Newton actually figured out calculus first. He was the first to work it out, but Leibniz was the first to publish. Okay, Leibniz was extremely brilliant man, but he was extremely rich. He was rich. he worked for Napoleon's army. So he was like, Napoleon hired him to oversee his French commandos in Egypt. This was in late 1600s, 16, yeah. Okay, and like, and he got really rich off of that. You know, war makes people rich, right? Okay, so he got really, really rich off of that, and Napoleon was like, "What do you want to do?" And he's like, "Well, I just want to study math the rest of my life." So he's like, "Okay, fine, here. We'll create a college just for you." So Leibniz was very rich from the war, okay, from the spoils of war at that time in history, and he just went and studied. He also came from a rich family, so not only was he rich, he was born into wealth, but he then accumulated a lot of wealth by working for Napoleon. Okay, Newton, however, was very poor. He was a very poor professor at Oxford University in England. So, yeah. So Leibniz, so even though Newton came up with calculus first to work this out, Leibniz had all the connections, and he was the first to publish. So they were bitter rivals. Newton's like, why'd you steal my stuff, bro? And Leibniz was like, I didn't steal your stuff. This is all my stuff. So I didn't even know you were working on it. And they actually ended up discovering calculus at the exact same time. It's kind of interesting. Okay. Newton was a physicist, and Leibniz was a mathematician. So they were actually working in different fields at the time. Newton was trying to figure out planetary motion, and Leibniz was just trying to figure out the area under a parabola. He was like, well, here's a parabola. What's the area under the parabola? That's all he was trying to do, find the area under that curve. Whereas Newton was actually trying to look at the celestial bodies and find the trajectory of the celestial bodies, which is tangential to tangent line to their position. Okay, it's tangential. Well, what's the tangent line? Well, it's the derivative. It's the slope of the tangent line is the derivative. So they were actually coming at calculus from two completely different vantage points, and they ended up actually getting there within about 8 years of each other. Newton just was not quick enough to publish. He wanted to spend more time working out his theories, and then Leibniz beat him to the punch, basically. And he's like, huh, I published, and you didn't. And so, yeah, they were bitter rivals to the very end. So, yeah. So, but what's interesting is that today, if you were to talk to somebody 300 years ago who discovered calculus, everybody would say Leibniz. But 300 years later, everybody says Newton. So I don't get it. Like, in 300 years, Newton actually, because he was the first to work it out, I guess, I don't know. He won in the end. He's like, I won, he won, even though he didn't get claim to fame when he was alive. He got it post hominus or something. I don't know how to say that. Post death. Okay, which is usually what happens to like artists and stuff. They get all their praise after they die, which is like, what's the point of that? Right? Okay, so let's do some second derivatives here. Okay, for y equals 1 over x, find y double prime. Okay, aka d2y over dx squared. Okay. So what's y prime? Well, that's negative 1 over x squared. I already know what that is. Okay, ooh, that's good. Okay, I should have that memorized. If you don't have it memorized, well, boo on you. Okay, you should have that memorized. But if you don't, what is this? This is x to the negative first power. Okay, that's what y is. And so what would y prime be? That would be negative 1 x to the negative 2, y prime, which is equal to negative 1 over x squared. Okay. So now I'm going to back up a step, and I'm going to look at this thing here, and I'm going to take another derivative. Let's do the second derivative. So I'm going to take the negative 2 and multiply it by the negative 1, making it a positive 2. I'm going to take the negative 2 and go down another power to x to the negative third power. So this equals 2 over x cubed. And that is the second derivative. Oh, okay. So what was the first derivative? It was this guy. What's the second derivative? It's the next guy. Okay. Let's look at the next thing here. Okay, 2. Okay. For y equals x squared plus 10x raised to the 20th power, find the second derivative. Okay, so let's look at the first derivative of this thing. That's going to be the chain rule, right? Okay, so y equals, first, y prime is equal to the first derivative, which is 20 times x squared plus 10x to the 19th power times the inside, which is 2x plus 10. Okay, so I'm going to look at it like this. Y prime is equal to 20 times 2x plus 10 times x squared plus 10x to the 19th power. Okay, distribute, and I get 40x plus 200 times x squared plus 10x to the 19th power. Okay, that's my first derivative. Now I have to do the second derivative. So the second derivative is a product rule, because I've got two functions there. I've got my first function and my second function. So let's do the product rule for the second derivative. Okay, derivative of the first, that's 40, times the second, x squared plus 10x to the 19th power, plus derivative of the second, that's 19 times x squared plus 10x to the 18th power, times the inside, okay, we're still not done with the derivative of the second, times the inside, that's 2x plus 10, times the first. Don't forget the first. That's 40x plus 200. Okay. So now let's factor this out. Okay. So what do I got? I've got, well, what do I have here? I have a 40 times x squared plus 10x to the 19th power plus 19 times 2x plus 10 times, I'm going to factor out a 40 here, times 40 times x plus 5. Okay, I factor out a 40 from this guy, and then that's going to be times x squared plus 10x to the 18th power. Okay, and there's a reason why I factored out this 40, because this has a 40, and this now has a 40. Okay, this has x squared plus 10x to the 19th power. This has x squared plus 10x to the 18th power. So I can factor out a 40 and an x squared plus 10x to the 18th power. Okay, what's left over is going to be an x squared plus 10x, one of those from here. And then I get this thing left over plus 19 times 2x plus 10 times x plus 5 left over. Okay. Interesting. So this thing becomes 40 times x squared plus 10x to the 18th power times x squared plus 10x plus, this is going to be 38x plus 190. Oops, no, that's not what I want. I could have done it that way, I guess. 38x plus 1, yeah, let's do it that way. 38x plus 190 times x plus 5. So I have to multiply this out, FOIL that out. So this is x squared plus 10x plus, this is going to be 38x squared, okay, plus 5 times 38 is 190, so plus 190x, okay, I think that's right. Is that right? 38 times 30, what's 38 times 5? 38 times 5, yeah, that's 190, that's correct. Okay, and then what's the next one? This is 190. Okay. So that's 190x, that's 950. Plus 950, okay, so let's clean that up. So x squared plus 38x squared, 39x squared. 10x plus 190x, that's, oh, plus 190x, so that's 380, 390. So that's 390x, so boom, 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 plus 950 times x squared plus 10x to the 18th power times 40 is equal to y double prime. There we go. So that was fun.
That was easy.
It actually wasn't, but it's all good. Okay, let's do some applications. The velocity of an object is the first derivative of its position at a given time. Okay? If r of t is the position vector, not vector, sorry, is the position of an object, sorry. You're like, what the hell's a vector? I'm like, sorry. If r of t is the position, I'm getting Calc 3 and Business Calc confused. Okay, if r of t is the position of an object, okay, then r prime of t equal to v of t, we call that v of t, is its velocity, and r double prime of t equals v prime of t equals a of t is its acceleration. Okay, it's acceleration. Okay, so the first derivative is velocity, the second derivative is acceleration. let's do an example here, number 3. Okay, after 5 seconds, oh, sorry, when an object falls, the distance is given by h of t, or the height, okay, is equal to 4.9 t squared, excuse me, the distance it falls, I guess I should say that when an object falls, the distance it falls is given by h of t equals 4.9 t squared. Okay, meters. Okay. Okay, find the position, velocity, and acceleration after 5 seconds of free fall. Okay, so we're up here on this cliff. Boom, that's me. Look at me. I'm awesome. What a handsome man. Okay, always smiling. Okay, and I drop something off of the cliff, right? Maybe, I don't know. What do you want to drop off your cliff? Maybe my sister. Okay, so I drop my sister, okay, off the cliff because she was a bitch. No, I'm just kidding. Okay, so, okay, there we go. Okay, so I can't kill family members, so just pretend there's a trampoline at the bottom, okay? Just, or maybe there's a pool with a bunch of sharks in it, okay? So with laser beams attached to their faces, okay? So here's the shark infested pool that I'm gonna throw my sister into. She was this, yeah, she stole my mom from me. But at least I'm not bitter. At least I'm not bitter. Okay, so she did. She literally stole my mom from me. She's like, she's mine, Jason. She's not your mom. She's my mom. Like, okay. So, like, whatever. So Thanksgiving, I just don't go to Thanksgiving anymore. We'll just put it that way. Okay. So there's my sister, and she's in free fall. Okay, and I want to know, how far did she fall after 5 seconds? Now I would have to have pushed her off a very high cliff for her to be free falling for 5 seconds. But let's see how much she travels. Okay, in this 5 seconds. Okay, so h of t is equal to 4.9 times 5 squared. Okay, so let's do h of 5. How far has she traveled? Okay, so that's going to be, okay, about 123 meters, I think. So let's see, 4.9. Okay, times 5 squared. Oh, that's times 25. Okay, 4.9 times 25 is 122.5 meters. Okay, just to get that in perspective for you people that live in America, okay, there's 3.3 meters per foot. Okay, so you would just want to divide this thing by 3.3. Oh, sorry, you would want to multiply by 3.3. So it's about 404 feet. Okay, so about 404 feet. Okay. It's not meters per foot. It's other way around. It's feet per meters. I don't know what I mean. Okay, it's 3.3 feet in a meter. Okay, so about 404 feet she would have traveled, okay, in the shark-infested waters below. Okay, so now how fast will she be going, okay, after 5 seconds? No. Sorry. You should ask me earlier. So I have money in my wallet. Okay. So do you want to see? You want to see what's happening? Never mind. Forget it. Okay. Let's. You guys are right. Okay. That you. I should not have doubted you. Okay. It's just. Yeah. Okay. Going back to. Yeah, okay, going back to the shark-infested waters, of which various family members are being thrown into at this point in time. Do you hear me? Shark-infested waters. That's what I thought. Okay. Okay, so what's the first derivative of this thing going to be? That's going to be the velocity, right? I'm going to see how fast these people are traveling. Okay. notice how happy I am. Okay, there's something wrong with this picture. Okay. So, okay. Crack myself up. Okay. What h prime of t, okay, is going to be what? Well, that's going to be 9.8 t. So that's the velocity. V of t is going to be equal to 9.8 t. So V of 5, the velocity after 5 seconds, notice that you travel faster and faster the farther you fall. So this is 9.8 times 5, 9.8 times 5. Okay, is 49. So this is 49 meters per second. Every second, she's traveling 49 meters per second. That's pretty fast because that's about 160 feet per second. So about 160 feet per second. These people are hurtling through the air at 160 feet per second. What's the acceleration going to be? What's v prime of t? What's the acceleration going to be? A of t. This is going to be 9.8 meters per second, which is, or meter per second squared. That's the acceleration. Why? Because what's the derivative of this guy? 9.8 t, that's 9.8. So the acceleration is always constant. You're always constantly accelerating 9.8 meters per second, which is basically 32 feet per second squared, which, why would you always be accelerating the same acceleration? Because gravity is always pulling you down at a constant rate. Acceleration due to gravity. Okay, so there you go. We got that one, and that one. Okay. Okay. Last example goes back to the last example in 1.7. I love it when everything kind of ties together. Remember what happened in 1.7, number 5. Number 5 of 1.7. We had our smartwatches. can't even spell. It's a dumb watch. Smartwatch, okay, N of T was equal to 250,000, this 250,000 after a certain number of weeks, right? 250,000 T squared over 2T plus 1 squared, right? And this gave me the number of watches sold after T weeks. It's the number of watches sold after T weeks. Okay, so this represents the number of watches. Okay, so let's run some numbers here. What was N of 52? What's N of 52? How many watches are being sold after 52 weeks? So I'm going to plug this in. 250,000 times 52 squared over 2T plus 1, oops, 2 times 52 plus 1 squared. Okay, so that's going to be 250,000 times 52 times 52. That's the top. That's a big number. So that's 676 million. I'm just going to write that 676 mil. Okay, and then this is over 2 times 52 plus 1. 2 times 52 plus 1, that's 105, times 105 is 11025, 11025, okay, which is approximately what? Let me take this number and divide it by this number. Oops. Okay, which is approximately 600 or 61,315 smartwatches are being sold that week. Okay, in the 52nd week. Okay, in the 52nd week, these are the number of watches sold. These are the number of watches sold in the 52nd week. It's not total watches. I don't think, was it total watches? The number of sold after 2 weeks. After 2 weeks. Maybe it is the total watches. Represents the number of smartwatches sold after 2 weeks. Yeah, I think it is total watches. We're just going to say it's the total watches. Total number of watches sold. Number is equal to the total sold after 1 year. Okay, 61,000. Okay, okay. It's good. Okay, what was N prime of 52? What did we find that out to be? Wasn't that about 22.5 from the previous example? Is that right? Right, we took the derivative, remember we took the derivative and then we put in 52 after 1 year, right? Okay, yeah, 22.5, okay. So this is the number sold. This is the total number sold. What is this? This is the rate of sales in rate of sales per week after 1 week. Or sorry, after 1 year. For 1 year. Okay, so every week we're going up by about 22.5 around the 52nd week. Does that make sense? After 1 year, we're selling an extra 22.5. What I want to know is what is N double prime of 52 and what does that represent? What is that? What is the value, but not just what is the value, what the heck does this mean? What does this represent? Okay, so let's do that. Let's take N prime of T and let's say that N prime of T was equal to, what was it equal to again? Wasn't it like 500,000 500,000 t over 2t plus 1 cubed. Wasn't that what we found that out to be? I think that's what it was. Okay, so this is from example 5. Example number 5 of 1.7. Okay. So now what we want to do is we want to do the quotient rule on this thing. So let's do that. Derivative of the top, let's do n double prime of t. Derivative of the top is 500,000 times the bottom, 2t plus 1 cubed, okay, minus the derivative of the bottom. Well, that's 3 times 2t plus 1 squared times 2. Okay, that's the chain rule, times the top, 500,000, okay, t, all over 2t plus 1 cubed squared. Okay, now I'm going to do something rather sneaky here. I'm going to clean this up just a tiny bit. I don't really care to clean it up a lot because I'm just going to plug in 52. Okay, I don't need to spend a lot of time cleaning up the algebra here. Okay, because I'm just going to be plugging in 52 anyway in my calculator and let the calculator do all the heavy lifting. So maybe I'll factor out a couple of things here. I don't know. We'll see. I don't want to get too much into this. But I could factor out a 500,000. I could factor out a 2t plus 1 squared, leaving me here a 2t plus 1 minus 3 times 2 times t. That's just minus 6t. Oh, that's kind of nice. This actually does clean up pretty nicely. Over 2t plus 1 cubed to the third, cubed to the second. So that's going to be to the 6th. This is 2t plus 1 to the 6th. Okay. So this actually does clean up pretty nicely. This is to the 2nd to the 4th. So this is equal to 500,000. This is 2t minus 6t, which is negative 1 minus 4t, all over 2t plus 1 to the 4th power. Oh, that's nice. So that's n double prime of t. But again, I just want to plug in at 52. What is this thing? What is n double prime at 52 at the 52nd week? So if I plug that in to my calculator, let's do that real quick. Okay, so I want plug this in, 500,000 times 1 minus 4 times 52, all over 2 times 52 plus 1 to the 4th power. So, okay, what's 4 times 52? 4 times 52 is 208. So 1 minus 208, 1 minus 208 is negative 207. Negative 207 times 500,000 times 500,000. Let's get the top. The top is going to equal negative 103,500. Okay. And the bottom is 2 times 52 plus 1 to the 4th power. 2 times 52 plus 1. No, that's not what I want. Plus 1. Okay, 105 to the 4th power. That's a big number. 121. Oops. Where'd my calculator go? 121, 550,625. Okay, and I'm going to divide those two numbers. Okay, so 103,500 divided by 121,550,625. And I get about 0.851. So this is negative 0.851. Okay, and what the heck does that number mean? That's what I want to know. Well, let's look at our scenario here, where we start selling a lot of smartwatches in the beginning and it kind of tapers off. So what does this mean? What is the second derivative actually telling me? Well, the first derivative, okay, the function value, okay, the n of t, this is how many watches I sold. How many watches, number of watches. Okay, what's n prime of t? Well, that's how fast they are selling. And what is n double prime of t? This is the acceleration or deceleration of sales. This is the rate of change of sales. Okay, it's the rate of change of sales. If it's positive, sales are going up. They're increasing. Okay, if it's going down, sales are decreasing. I'm selling less and less. It's the rate of change of the sales, the daily sales. Maybe I should put daily or weekly sales. Sorry, rate of change of weekly sales. So as I hit this 52 mark, how many watches did I sell? How many total watches have I sold? Oh, n of 52 was equal to 16, what was it back here? 61,315. 61,315. Okay, 61,315. That's the total number of watches sold. Total watches. What was n prime of 52? Well, that's how many more I'm selling each day. This is 22.5 more per day. And what was n double prime of 52? Well, that's negative 0.851, negative 0.851 watches. I'm sorry, this is per week. Okay, watches sold per week. What does that mean? That means that the number of sales is decreasing. The amount that I'm selling is going down. I'm losing sales each day or each week. It's negative. Now, what is this? How am I losing sales? Well, let's say that at the 52nd week, I sell 22 watches. But on the 53rd week, I only sell 20 watches. Well, I still sold watches, but what happened? Didn't I sell less watches? Does that make sense? So this is a decrease in sales per week. It's a decrease in sales per week, which is the acceleration of sales. It's basically a deceleration. Sales are declining. Sales are declining. They're going down, right? Even though the total number of watches being sold is going up, and even though the number of watches being sold is positive, the momentum is slowing in our graph. That was the bad graph. Okay, the momentum is slowing. And so every week, I sell fewer and fewer watches. Okay, fewer and fewer and fewer watches until I finally cap out at around 50,000, or sorry, 500,000 watches. I can never get beyond that asymptote. Okay? Okay,